Today I want to talk about electromagnetic interactions in terms of spins. There are two examples I want to do. One is minimal coupling, and the other is the Aharonov-Bohm effect. Classical electrodynamics tells us there's a Lorentz force law. Whenever I have a particle of charge Q passing through an electric and magnetic field, there's a Lorentz force that's placed on it, which is equal to the sum of the electrostatic force and the magnetic force. But in this case, we can't express this force in terms of a gradient of a potential energy. So that means we can't use the time-independent Schrödinger equation. Nonetheless, we can still use the time-dependent equation. This will work. If I have a charged particle with momentum p that's subject to a magnetic field and an electric field, my Hamiltonian is transformed into 1/2, 1/2m p minus qa squared plus q phi. You can write my phis like this to indicate that it's different than the coordinate phi. A, in this case, of course, is the vector potential, magnetic vector potential. And this phi represents the scalar potential. I can write E as minus, my electric field is minus del phi minus dA dt. I can write my magnetic field as, of course, del cross A, the vector potential. And, of course, I'm going to represent my momentum in the quantum mechanical way as IH bar del. That turns my Hamiltonian into something that looks like this. H is equal to 1/2m minus IH bar del minus QA squared plus Q phi. My Schrödinger equation then becomes IH bar d psi dt equals 1/2m minus IH bar del minus QA quantity squared plus Q phi times psi. This is what we call the minimal coupling rule. And I can solve the Schrödinger equation from there. So this is a nice way of expressing the effects of the Lorentz force in a quantum mechanical system. What I'd like to do next is use this coupling to talk about an effect called the Aharonov-Bohm effect, and this one will absolutely surprise you. So in classical electrodynamics, my potentials A and phi are not uniquely determined. The physical quantum, when we're talking about classical E and M, we think about the fields E and B as being the physical quantities, and sometimes we look at A and phi as potentials that are basically useful to calculate the observable fields. Things are going to get turned around on their head when we talk about them in quantum mechanics. We talk about the fact, if I apply a gauge transformation to my scalar potential, where I subtract d lambda dt from my initial potential, and I add some gradient of lambda to my vector potential. My fields that result using the equations for E and B, my fields are going to be not, invariant. They're going to be the same. We call this condition gauge invariance, and it's extremely important all through particle physics, condensed matter theory, and so on. So when we move over to quantum mechanics, though, it turns out that it's the potentials and not the fields that carry the day. The theory remains gauge invariant, and it can be shown that psi prime is equal to e to the I q lambda times psi. And it will still solve IH bar d psi dt is equal to 1 over 2m minus IH bar del minus QA all squared plus Q phi times psi. Now, since psi prime differs from psi by only a phase factor, they both represent some physical state. So the quantum mechanical theory is still gauge invariant. So for many years, the common wisdom was that there are no electromagnetic influences in regions where E and B are zero. But Bohm and Aharonov showed that this isn't correct. In fact, they did it in 1959. Turns out that the vector potential can affect the quantum behavior of a charged particle even if the particle is in a region where the field is zero. Well, how can this be? Let's look at the following example. Suppose we have a particle moving in a circle of radius b. So it's a charged particle, kind of like a bead on a wire ring. And suppose I have a solenoid of radius a running down the middle of this circle. So it's got this radius a. And it creates a magnetic field. Of course, it's a very long, almost ideal solenoid, so the field is parallel to the direction of the coil, and it's uniform inside. Outside the coil, we expect that the field would be zero. We're obviously going to put a current through this coil so we can create the field. And we expect, as I say, it's going to be uniform inside, and outside it's going to be zero. However, the field out, the vector potential outside of the solenoid is not zero. We're going to adopt a gauge convention that del dot A equals zero. That means I can write A as equal to some magnetic flux divided by 2 pi r in the phi direction. Notice we're not talking about electric potential, this is phi, the coordinate, for r greater than A. So outside the solenoid. Phi, the magnetic flux, of course, is equal to the area, pi r squared, in this case pi a squared, times the magnetic field. That's the flux through the solenoid. Field, remember, is equal to B inside the solenoid. Also, the electric potential is going to be 0 since the solenoid's uncharged. My Hamiltonian for this becomes 1 over 2m minus h bar squared del squared plus q squared a squared plus 2I h bar q a dot del. But the wave function depends only on phi, since theta is pi over 2 and r is equal to b. So del just becomes unit vector phi divided by b d phi. My Schrodinger equation then becomes 1 over 2m minus h bar squared over b squared d squared dp squared plus q capital phi over 2 pi b squared plus I h bar q over pi b squared d phi, operating on psi of phi, and that's going to be equal to E psi of phi. Okay, that's a mess, but it is a linear differential equation. It's got constant coefficients. So I'm going to write it like this. Second derivative of psi with respect to phi squared is minus 2I beta d psi d phi plus E psi equals 0, where I'm going to define epsilon as 2mb squared capital E divided by h bar squared minus beta squared. And beta is going to be defined as q times the flux divided by 2 pi h bar. The solution to this equation looks like psi is equal to a e to the I lambda phi, where lambda is equal to beta plus or minus square root beta squared plus epsilon, or beta plus or minus b over h bar square root of 2 me. Now for psi to be continuous at phi equals 2 pi, lambda has to be an integer. That means beta plus or minus b over h bar times the square root of 2me is going to be equal to some integer n. The energy associated with that, E sub n, then, is equal to h bar squared over 2m b squared n minus q phi over 2 pi t squared. And n can be 0, plus minus 1, plus minus 2, etc. So the solenoid has twofold degeneracy. The plus n represents a particle traveling in the same direction as the current in the solenoid and has a lower energy. The negative n describes a particle that's traveling in the opposite direction of the current and thus has a higher energy. The allowed energies depend on the field inside the solenoid, even though the field at the location of the particle is 0. That's interesting. So suppose, let's do this. Suppose a particle moves through the region where B is 0, but A is not 0. A is not 0, B is 0. My Schrodinger equation, 1 over 2m minus I h bar del minus QA squared times psi is equal to I h bar d psi dt. I can simplify this in the following. I'm going to write this as psi is equal to e to the ig psi prime, where g is some function of r and is equal to g over h bar integral from maybe some reference point, which I can arbitrarily choose, to infinity. I'm sorry, to r. Sorry. A of r prime dr prime. Now, del psi is equal to e to the ig, which is equal times I del g psi prime plus e to the ig del psi prime. But del g is equal to QA divided by h bar. So what do we get? Minus IH bar del minus QA times psi is equal to minus IH bar e to the IG del psi prime, or minus h bar squared over 2m del squared psi prime is equal to IH bar d psi prime dt. So psi prime satisfies the Schrodinger equation without A. If we can solve it correcting for the presence of a curl-free vector, we just take on this phase factor e to the ig. Let's see how this works. Suppose I take a beam of electrons and I split it. Split the beam of electrons in two. Let the beam pass on either side of the solenoid before the beam recombines. So the beams only see the region where B equals 0, but A is not equal to 0. So the two beams arrive back together with different phases. You can write it this way. G is equal to Q over H bar integral of A dot R. I can write that as Q phi 2 pi H bar integral 1 over R phi hat dot R phi hat d phi is equal to plus or minus Q phi over 2H bar. The plus sign applies to the electrons that are traveling in the same direction as the vector potential, in other words, a solenoid current. And the beams arrive they arrive out of phase with respect to phi. The phase difference, Q phi over H bar, is confirmed experimentally. This tells me that these beams arise out of phase even though there's no electric field to affect, no magnetic field affecting the beams. It's only the vector potential, magnetic vector potential, that affects these beams and causes this phase difference, causes the beams to arrive out of phase. And that's the sum total of the Aharonov-Bohm effect. So it's a very interesting effect. It leads to some extremely interesting properties in quantum mechanics called Berry phases, and which have application in all kinds of areas, condensed matter field theory and others. And so we'll touch on Berry phases at the very end of the course and bring back some of the concepts from this Aharonov-Bohm effect.